Good afternoon, everyone. It's great to see you here, both attending in Physics MP 102 and also online. Do you hear feedback coming through the microphone at all? Okay, I'm hearing a little bit, but it's just a local source. So it's my pleasure today to introduce Professor Aditi Sheshadri from the Department of Earth System Science at Stanford University. Aditi is an atmospheric dynamicist. So there's one atmospheric dynamicist at Stanford University. Aditi is that person. And this is a really important area of research to explore within kind of the larger setting of climate science. Aditi was trained, got her PhD at MIT, and after postdocs at Columbia University as a Simons Junior Fellow, she joined the faculty at Stanford in 2018. And as we've been talking about, in the intervening period, there was a pandemic you might have heard of. And so we're sort of just emerging from that. But through that program, Aditi's research has really shone and really expanded. And she has a very active research program at this interface between atmospheric processes and machine learning that she's going to talk about. And although today she'll be focusing on atmospheric gravity waves, her research interest spans a wide range from these relatively small scale waves that we're talking about today to the very largest scales. And I think what you'll hear today touches on those interconnections. So they're very interesting. So I just want to remind everyone that after the colloquium and our Q&A, we'll have a post-colloquium coffee. So you're welcome to join us, even those who are in the building and just listening online. You can come down and grab some coffee if you want to keep chatting with Aditi. And with that, I'll ask Aditi to talk about an improved understanding and representation of atmospheric gravity waves. So please join me in welcoming.
Thanks so much, Paul, for the introduction, and to everyone for showing up and online as well. I'm going to be talking through most of my talk on these atmospheric gravity waves, which are incredibly tiny, but then have a significant impact on planetary scale motions. So here's just a little image to kick things off. This is showing you some of these atmospheric gravity waves and these beautiful cloud patterns off the coast of Africa. So these are quite ubiquitous. If you look at satellite images, things like that, you can see them quite a bit. But for the students in the room, just to kick things off, I like showing this beautiful image of the Earth from space. And if there's only one thing that you take away from this talk, what I'd like you to remember is that the small scales of motion in the atmosphere really impact the large scales of motion in the atmosphere. And you can see that geophysical fluid dynamics, so just looking down at the Earth from space, there's this whole range of length and time scales that are of importance. So if we just look down at the clouds, you can see these tiny poofy clouds over the ocean. But then you can also see organized bands of clouds. I'm gesturing over the Atlantic basin and over the Pacific as well. So these indicate the position of the jet stream in both basins. And so geophysical fluid dynamics is multi-scale in both space and time. So motions on small scales and very high frequency motions can actually impact a planetary scale things like the jet. So people like me, we are fluid dynamicists, and also we're all mostly modelers. So we're very interested in a whole hierarchy of climate models. So what all of this means basically is that we take the Earth, we divide it up into these little grid boxes, which are typically something like 100 by 100 kilometers. So this model wouldn't know the difference between, say, Boston and New York. It's all in one grid cell. And in each of these grid cells, the Navier-Stokes equations are a version thereof. So it's just conservation of mass, momentum, and energy are stepped forward in time. And while doing that, there's a whole host of processes that basically fall through the cracks. So there are things like clouds, convection, and these waves that I'm going to be talking about, atmospheric gravity waves, that vary on length scales and time scales that are too small to be resolved by these global climate models. And so we have to put in sort of a best guess of what we think these scales that are not resolved are doing to the scales that are resolved. So if you talk to a lot climate modeling people in the present moment. They're all working on some version of this problem. And my version of the problem is atmospheric gravity waves. I should say at any point, if someone has questions, just put your hand up or just yell at me. I'm much less nervous when you actually talk to me. So that's good. Okay, so the atmospheric gravity wave part of my talk is going to consist of these 3 segments. We've been tackling this problem using a whole range of tools in my group over the last couple of years. All of this really blossomed during the pandemic, it would appear. The first part is going to be basically throwing out the conventional gravity wave representation and models and replacing it with a completely machine learning or a data-driven gravity wave parameterization. The second part of my talk will be about calibration and uncertainty quantification, which is something that you're going to hear about a lot across a whole range of fields at the moment, uncertainty quantification. So the idea there is the following. So we make approximations in GWPs. So let's say there's a number which we decide to be 4 meters a second based on the observations. And then we take that number and we push it through the whole climate machine. And then at the end, the climate projection under a double CO2 scenario will say that the extreme rainfall over California changes by some %. Now, supposing we got that number wrong to begin with, and there's actually a whole set of numbers that actually matches observations, or it was not 4 meters a second, it was 6 meters a second, how does that change the output of the model? So that's what I mean by uncertainty quantification. And more generally, what I mean is that we want to carry through PDFs of variables through the whole model rather than just one number. And I'll introduce a way to do that in a very systematic manner that seems to work very well for this specific problem again. In the third part of my talk, I'll tell you about some pretty exciting new observations, not from a scientific campaign by any means. These observations come with very large error bars, but I'll tell you about some very patient work done by a couple of my postdocs to try and extract gravity wave motion, extract information about what gravity waves do to the mean flow based on these observations. If by some chance I get through the first part of my talk, I have about 10 minutes on this project that I've been working on my own. So no students or postdocs involved, and so it's moving along rather slowly, kind of by definition. But I found myself, this is kind of my COVID project. I found myself thinking about, we're all familiar with the weather. And if the forecast says it's going to rain tomorrow, we're going to take it kind of seriously. But then if it says it's going to rain in 10 days time, we know not to take it very seriously. So I found myself wondering what sets that 10-day time scale. And would that 10-day time scale change in a warmer climate, in a cooler climate? So, I have a short paper on this with some new results. So if I manage to get to that, I'll tell you about this stuff. So let me just jump into gravity waves to begin with. This is a physics audience, so I should say that these are not gravitational waves. I am not talking about fluctuations in space-time. What I am talking about is basically buoyancy waves in the atmosphere. So you can think about tossing a pebble in a pond, something like that, and it sets off waves. It's much the same thing. So the atmosphere is stacked up in these layers which are stable to vertical motion. And there are all kinds of things which can perturb the atmosphere away from that state. You can think of things like flow over orography. So when flow moves over mountains, there's all of these other things that I've listed, but you can think of storms in the tropics being a source of these atmospheric gravity waves. When motion of different scales in the atmosphere interact, which we call eddy-eddy interactions or wave-wave interactions, that can set off atmospheric gravity waves. Geostrophic adjustment of jets. There's basically atmospheric gravity waves are ubiquitously forced everywhere in the atmosphere. And then they propagate away from their source, both in the vertical and in the horizontal. And much like waves break on the beach, which everyone is familiar with, these waves break at some point in the atmosphere. When they do that, they deposit their momentum within this breaking region where the waves are breaking. And so they can provide either an acceleration or a deceleration on the mean flow in that region. Gravity waves are a really nice example of the multi-scale nature of GFT. Because they can vary from length scales of 1 kilometer to planetary scale. So that's 10 to the 5 or like 10 to the 6 kilometers. So that's 5 or 6 orders of magnitude. They also have a whole range of frequencies. They can be very high frequency waves. There are also more slowly varying waves. And because of the fact that they have this wide range of length scales, they mostly fall through the cracks of a grid box of a typical global atmospheric model, which is about 100 by 100 kilometers. This is showing you an example of these gravity waves. This is 60 hectopascals, so quite high up in the atmosphere. This is at the equator. What you're looking at is Hofmüller diagram. So just basically showing you variations of a variable with the time mean taken out. We've got longitude on the x-axis and time is advancing on the y-axis. So you can see these quite small fluctuations in both of these images. And these are symptomatic of these atmospheric gravity waves. I am beginning to think that we should just call them buoyancy waves to avoid confusion. So as I've said many times now, these are quite small, but they're crucial in atmospheric dynamics. We think that the momentum from these breaking atmospheric gravity waves produces about a third of the forcing of the jet stream, which is a huge planetary scale phenomenon. They're also really crucial in this QBO phenomenon. Has anyone heard of the QBO before? 1, 2, 3, 4. All right. So it's the quasi-biennial oscillation. It's a really large scale. Its period is of the order of 18 months or so in the tropics. And the winds actually reverse in they blow from one direction and then they blow from the other direction every 18 months in the tropics. It's this pretty large scale oscillation. And we think that it influences things like rainfall over the tropics in the troposphere. This is up in the stratosphere, which is about 10 kilometers and above the surface of the Earth. So we think that that atmospheric gravity waves are really crucial in forcing this QBO. They also play a very important role in polar vortex breakdowns, like when you have a particularly crappy winter, when you see these CNN articles about the polar vortexes back, atmospheric gravity waves play a role in that process as well. So long story short, these waves are forced everywhere. They propagate both vertically and horizontally. They have a large range of length and time scales associated with them. At some point, they go and break. And so they force the mean flow. Any questions on any of that? Yes. Yes, yes, exactly. Right. So the question was, are there actual density variations? Yes. Yes. So you're displacing a little parcel of air upwards, say, and then it comes back, but it overshoots, and that, yeah. Yes. Well, yeah, buoyancy is probably a better definition because, yeah. Okay, so these atmospheric gravity waves are a huge source of uncertainty in climate models, in saying what the climate would look like in 50 years or 100 years or anything like that. And the reason that I got into this is that unlike clouds, it was getting very little attention from the climate modeling community. Gravity waves, this gravity wave representation problem has historically had a bunch of approximations associated with it. The chief amongst which I think is that all climate models only permit these waves to propagate straight up. They are not permitted to propagate in the horizontal at all. There is no climate model today that permits these waves to propagate horizontally. These GWPs are not observationally validated. There isn't a good global source of observations telling us what these waves are actually doing to the mean flow. So GWPs are not well validated from observations. There's some satellite data, but not a whole lot, and not at the time and spatial scales that we need. And GWPs in climate models are based on under-resolved sources such as convection. So convection is itself parameterized. And so that's another problem. So this is showing you just how bad this situation is. This is from the Canadian climate model, which I thought you guys would like. This is from back in 2010. This is two versions of the model with equally defensible choices of gravity wave parameters on the left and in the center. So this is the change in the sea level pressure, which is a pretty basic quantity. Under a double CO2 integration, the only difference between this and this is just choices in the approximations made in the GWP. This is the difference between these two. So you can see that just this one parameter changing gives you a huge difference in something as basic as sea level pressure over the Arctic, both in terms of the sign and the magnitude of the change. So this is quite a serious problem. Other climate models behave somewhat similarly. So I'll just jump into the research aspects of what I'm going to be telling you about. To begin with, I'm going to be telling you about just throwing out a GWP and putting in its place a completely machine learning or a data-driven version of this. The hope with this, of course, is that we can train the ML-based parameterization on some combination of observations and very high resolution model output, and then put it back into a model with your typical 100 by 100 kilometer grid spacing, and then have a representation of what's happening in a very high resolution model in a low resolution model. That's the hope. So let me get into that. We're going to be playing around for the first two parts of my talk with a model that I'm going to be calling MEMA, the model of an idealized moist atmosphere. This is based on GFTL's state-of-the-art model. So it's AM4, it just doesn't have a coupled ocean. So the ocean takes ages to come into equilibrium. So this is a fairly good simplification. It has a good radiation scheme. This refers to the horizontal resolution. So this is T42 for those in the know. It's about 300 by 300 kilometers at the equator, and it's got 40 levels in the vertical. Importantly, it has implemented within it this Alexander and Dunkerton gravity wave parameterization, which basically mimics the time and space average effects of many discrete intermittent packets of breaking gravity waves. And so all it does is that it adds on a drag to the X and the Y direction. It is single column, but we have to start somewhere. So we are going to try to build an ML-based parameterization, which does as well as 8099 in MEMA. Here's the architecture that we used. I'm sure there must be ML buffs in the audience because there are typically everywhere that I go. So here's the architecture of the NN that we used. We gave it everything that we could think of to begin with. I'll present some additional feature experiments in a couple of slides, but we gave it wind along both directions, actually wind along all three directions, the temperature, the height, the location, and the surface level pressure. And all that the NN is trained on is the output from this 8099, which is just drag in two directions, X and Y, along the column. Okay, is that clear? I'll assume it is. So here's the NN architecture. It seems to have a large number of these 3.8 million total parameters. But we have an analysis of how complex this thing needs to be in this paper, and we can get away pretty well with about 500,000 of these, which isn't too deep of a network really. I could show you more quantitative metrics, but I'm just showing you a year of drag from the model. So what we're looking at is drag in the X direction on top and drag in the Y direction at the bottom. We've got WaveNet. So this data-driven GWP, we decided to call it WaveNet. We thought it was a nice name. So we've got WaveNet on the left, 8099 on the right, and the difference between the two in the center. This is the subject of an ongoing discussion with my student Zach, who likes the difference in the center. I would have preferred it on the right, but anyway, he won out. So I could show you R squared or like any measure that you're interested in. And basically, WaveNet is doing a pretty good job. It gets the annual cycle of drag. So what I'm showing you here is at 100 hectopascal. So it's high up in the atmosphere, kind of where the jets sit at a maximum. And it's doing pretty well. This is the annual cycle of drag. The differences here are actually quite minimal. So WaveNet is doing a pretty accurate job. The other thing is that WaveNet appears to be reasonably generalizable. So we've trained WaveNet on only 1 year of output. So it's only seen one phase of this quasi-biennial oscillation. It's only seen the westerly phase. So the winds are blowing from the west is all it's seen, and that's all it knows. What I'm showing you here again is a drag in the equatorial region that drives this oscillation. On the top is 8099, on the bottom is WaveNet. And WaveNet has only been trained in 1 year. And so WaveNet, having been trained in only 1 year, is able to complete the oscillation, to initialize the easterly phase of the oscillation, as well as reinitialize another phase of the oscillation. So that's pretty good. I've highlighted places where the drag is a little bit overdone by WaveNet, but I think that this is easily fixable by just training it perhaps by being a bit less severe with WaveNet. If you actually show it snapshots of the easterly phase, this isn't a problem anymore. I promised you some feature experiments, so here they are. And what I mean by feature experiments is that instead of giving WaveNet everything that we could think of, we only gave it certain subsets of the input. There's an accompanying SHAP value analysis in the paper, which I would encourage you to check out. What SHAP values do is that they tell you the incremental value of adding on another variable to your NN. And SHAP values permit some kind of interpretability. And what the SHAP values have told us from this analysis is that WaveNet, what WaveNet seems to be doing is learning some kind of link between the drag and the mean flow. All WaveNet really needs to output the drag is the flow above and below where you are, which to us lines up pretty well with so we understand what atmospheric gravity waves do. We have theory for what they do. And what WaveNet is doing seems to correspond pretty well with our understanding of what atmospheric gravity waves do. What I'm showing you here is R squared as a function of pressure on the y-axis for these different feature experiments. So to just tell you the point of this slide, all that WaveNet needs to give you the drag in the x direction is the wind in the x direction. And all that it needs to give you the drag in the y direction is the mean wind in the y direction. This isn't particularly surprising because 8099 is a somewhat simple gravity wave parameterization, but that WaveNet is able to do what 8099 does with just 1 year of data. We think is quite promising. I think you've had Laura Zena come and talk in the last year, and you also had Raf Ferrari come and talk in the last year, and they've been doing sort of similar things with ocean eddies. And previous such attempts to couple ML algorithms with climate models have resulted in several challenges. The first, which I do not mean to minimize by any means because it took us 6 months to overcome, is that climate models are in Fortran. Anyone here familiar with Fortran? That's more than I typically get. So climate models are in Fortran, ML is in Python, and so getting Fortran and Python to talk to each other was actually a bit of a nightmare. What we did was use 4Pi, which is this interoperability package. We're in the process of rewriting the entire ML in Fortran, which works better than doing this. But this is a great sign. We have now coupled WaveNet back into MIMA. So each time that MIMA needs a drag from these breaking gravity waves, it calls on WaveNet. WaveNet supplies the drag. And we now have hundreds of years of integration. MIMA with WaveNet is stable and accurate when WaveNet is online, which is absolutely wonderful. We have 300 years or something of stable integration now, and this is the QBO. On the top, I believe, is 8099, and the bottom is WaveNet. The period with WaveNet is pretty good. It's within a 1 standard deviation of what it is with 8099. It is overdoing the westerly amplitude, but again, it's only seen the westerly amplitude, so this isn't that surprising. We think we fixed this now, but I don't have publishable results from that yet, so I won't show you those quite yet. And the last thing that we did was to show WaveNet CO2 concentrations, which it had never seen before. WaveNet is trained on a climate like today, and we went ahead and we quadrupled the CO2 concentration. I think we can forget these top panels and just focus on these two bottom ones. What I'm showing you here is the response of the circulation of the atmosphere to this quadrupled CO2. So this is zonal mean, zonal wind. So the mean wind around a circle of latitude as a function of latitude and going up into the atmosphere. So this is MEMA's response with 8099, and this is MEMA's response with WaveNet. The fact that it did not completely blow up and refuse to run, to me, was a win. The aspects of the climate change response, which we think we understand, including the poleward shift of the jets in the troposphere, is captured by WaveNet. With 8099, the QBO period goes up, so it does with WaveNet. The polar vortices as well seem to intensify with 8099. They do as well with WaveNet, but then the intensification of the westerlies is not quite as uniform across the depth of the atmosphere as it is with 8099. I should really emphasize here that what WaveNet is doing is attempting to do just what 8099 would have done. This is not telling us anything about the response to an increased CO2 climate. It's just doing whatever 8099 would have done. But it seems to generalize. It is accurate. It is stable. I mean, it's accurate whether it's qualitatively accurate, and it is stable when MEMA is coupled with WaveNet. Just wanted to highlight that all of this work was done by Zach Espinosa, who started working with me as an undergrad a couple of years ago. He's really just phenomenal. But the paper's out in GRL earlier this year. Of course, we're going down all kinds of different lines with this research, including training WaveNet on high resolution output and observations rather than the model itself. So that's where we are on this front. Any questions before I move forward? Okay, so I'm going to tell you about calibration and uncertainty quantification as a next step. One approach is to throw out the existing GWP completely, which is what I just showed you. But realistically, all climate models, all climate modeling centers will have some version of this going forward. And the way that they do this now is that they just set these numbers manually to get you a climate that looks like today. So we'd like to throw that out the window and come up with a more systematic way of calibrating these parameters. So that's what this is going to be about. We're going to stick here with MEMA and 8099, and I'm going to tell you a bit more about 8099. Just bear with me. So what 8099 does is that it launches these waves with a spread of phase speeds. This is the momentum flux associated with what's set off by 8099. And it has this parameter CW, which is a half width of a Gaussian distribution, which is just calibrated manually. So a CW will just be some number. Similarly, it takes into account the intermittency of these waves through this intermittency factor epsilon, which has another parameter, which is the total gravity wave stress, which I'm going to call BTEC. So this is close to the equator because I'm going to focus on the QBO again. So there's this half width of the phase speeds and the total gravity wave stress near the equator. Neither of these are well validated using observation. So they're just two numbers that the lab pulls out of thin air, presumably to give you a reasonable climate. And I'm going to try and calibrate these parameters to give us a reasonable QBO. And by a reasonable QBO, I just mean a QBO that has a reasonable period and a good amplitude. So you can think of the inverse problem as being something like this. Y just consists of the period and the amplitude of this oscillation. The theta can consist of just these two parameters, the half width and the total gravity wave stress. And the epsilon here is internal variability associated with the model. G is our MIMA, so the forward integration of MIMA. This is our very expensive forward model. So is this bit clear? Great. And I'm going to use an approach which has been referred to as this three-step Calibrate-Emulate-Sample approach. It's been laid out in some detail in this JCP paper last year. I think Graf Ferrari's group has been using something similar for ocean eddies. So penetrative convection in the ocean, for instance. And there's been this paper out of Tapio Schneider's group doing it for convective parameterization. It seems to work reasonably well in both of these situations. So we're going to go ahead and apply it to our problem. And I'll talk you through the approach and then talk you through the approach for our specific problem. And then you can ask me questions. So the first part will be this calibrate step, which will use ensemble Kalman inversion. It's sort of like data assimilation, but not really. What it does is that it minimizes a cost function, which is the difference between the QBO period and amplitude that you would like and what your model gives you. And it pushes these two parameters, which I mentioned, CW and BTX, towards values that bring the model output closer to what we would like it to be. So it just defines a cost function, and at each step of ensemble Kalman inversion, or ECI, it sets off an ensemble of MIMA integrations. We do 20 runs per ensemble and pushes it closer and closer and closer to what we would think of as the truth. You can use whatever you want as a truth. You can use observations. You can use a long run of the model. You can use whatever you want. Having done that, we have a large number of forward integrations of the model, which we can then use to build a Gaussian process emulator, which you can think of as pretty much a theory. It's not quite a theory, but it's a map between the values of these two numbers, CW and BTX, and your output, which is the period and the amplitude of the QBO. That's this step. Having done this, we can now sample from a posterior PDF and actually get uncertainty quantification associated with the model in the future. Okay, so if that's not quite clear, I'm going to talk you through it for the specific example. Here we go. This is the ensemble Kalman inversion. What I'm showing you here is 10 iterations of ECI. At each iteration, ECI sets off 20 model integrations of MIMA. On the top, you can watch the half width and the total gravity wave stress get closer and closer to the truth. At the bottom, you can watch the things that we're trying to optimize, which is the period and the amplitude of this oscillation, again, get closer and closer to the truth. What I'm showing you here is just optimizing based on a long run of MIMA, but you could use observations instead, we have, and it works pretty well. The nice thing about ensemble Kalman inversion and these Bayesian methods in general is that you can take along one standard deviation with you through the whole process. So those are these dash bars over there. Ensemble Kalman inversion converges at infinity. And so at some point, we just have to call it. This is 10 iterations of ECI that I'm showing you. Having done that, we now have, with each iteration, we have 20 times 10, 200 integrations of MIMA. We can use that to train this Gaussian process emulator, which is a cheap way of evaluating what would MIMA do if the half width was something and the total gravity wave stress was something. What would MIMA do in terms of the QBO period and the amplitude? Having done that, on some of these integrations, we can then test on the ones that we didn't train the GP emulator on. So that's what I'm showing you. This is the test of our Gaussian process emulator, and it seems to do pretty well. Having done that, we can now build these lovely contour plots. So on the top is the QBO period as a function of the half width on the x-axis and the total gravity wave stress on the y-axis. I gave this talk at GFTL, and Isaac said, okay, so you now have a theory for the QBO. It's not really a theory for the QBO, but it's a map that maps these two things, the half width and the total gravity wave stress, to the two things about the QBO that we care about, the period and the amplitude of the QBO. And as I said, this takes along one standard deviation with it. So that's what that looks like. Having done that, we can now sample these contour plots to put us in the neighborhood of what we would want the period and the amplitude of the QBO to be. So we want the QBO to be in the range of what we think of as the truth. So we set off an MCMC, a standard walk metropolis, which is sampling the space. You can watch it go through the space. So it's tracing out the region of phase space, which is in the region of what we would want the period to be. And similarly here for the amplitude. If you watch this evolve, it takes on a PDF, which looks a kind of a little bit like a banana. So Laura and I have been calling this the banana PDF. Here's a banana PDF. So this is the joint PDF down there, which looks like a banana. On the top and the bottom are the conditional PDFs. So the blue is our prior. I should have mentioned that we start off with a log normal prior because we expect both of these numbers to be positive because they have to be. The blue is the prior. The gray bars are the posterior distribution that we get from our analysis. And this green line here is the truth that we're trying to get to. So I think this is kind of interesting. You can get a pretty wide range. We haven't narrowed the posterior on the half width like at all. We have quite a bit on the total gravity wave stress. So what this is telling us is that there's a pretty narrow range of total gravity wave stress, which gives us a meaningful QBO at the equator. And you can have a pretty wide range of half width, the phase speeds of these waves in the deep tropics, and also get a reasonable QBO. Now, having done this, we can sample sets of parameters from this posterior distribution and then run sort of short integrations of MEMA to actually put uncertainty bounds on the period and the amplitude of the QBO in a quadruple CO2 climate, which is what this is. And that's different from internal variability. It's the uncertainty that comes from picking these parameter values. So going forward, all climate projections, I think, ought to include estimates of uncertainty associated with the choices of numbers like these. The papers in minor revision at James, we're nearly there. I think it should be accepted very soon. And also wanted to highlight that Laura Mansfield, my postdoc, has done much of the work on this aspect of the talk. Questions, anyone? Okay. All right, so I'll tell you a little bit about observations. I'm mostly a theorist and a modeler, and I don't do very well with observations, but I'll just show you some snapshots of observations before I move ahead. How many people have heard of Project Loon? That's not fair. One, I think, was the answer. Okay. So Project Loon came out of Google X, which I believe is just called X now, just to make it extra mysterious, I suppose. But Google X used to be Google's sort of research division. It's a very interesting building to visit. I highly recommend it if you ever have a chance. The parking lot is full of self-driving cars. You have to be escorted pretty much everywhere in the building, and they have these micro kitchens on every floor. I was kind of glad that they didn't call them nano kitchens, but it's an interesting building. So they were putting these balloons into the upper atmosphere, so the upper troposphere, lower stratosphere. They started back in 2013. They were launching from New Zealand because they were the only ones who would allow them to launch from their country. And I encountered them when I was at a Spark meeting in New Zealand when I was a student. So between 2013 and about 2021, they in 2017 or so, they were given permission to launch from San Juan, Puerto Rico, as well as somewhere in Nevada. And there's of the order of 1,000 balloon flights between 2013 and 2021. Just to emphasize, this is not a scientific ballooning mission. It's just that they had GPS on board these satellites, and they just happened to measure latitude, longitude, height, temperature, and pressure about every 60 seconds. In some cases, it's more frequent even than 60 seconds. There have been previous scientific ballooning campaigns to measure atmospheric gravity waves, but they've typically involved a dozen balloon flights or so with very good data, but they're just about a dozen balloon flights, and they're geographically very constrained in where they go. This is what Loon looks like in contrast. This is color-coded by month, January through to December. And this is about 1,000 balloon flights, maybe a bit more. You can see that there's really good coverage over the Southern Ocean region. There's pretty good coverage over the tropics, even over North America and the Americas in general. There's pretty much no coverage over Western Europe and Asia. And I think that's mostly coming from the fact that Russia, China, and India would not permit these balloons to enter their airspace. But with all of the shortcomings, this is still pretty much global coverage. And it's very high resolution data because they were taking data every 60 seconds. And so we are using these balloon flights to back out momentum fluxes transported by these atmospheric gravity waves. Doing a wavelet analysis actually lets us get down to wave packets. So it's been an interesting couple of years. This paper from my former postdoc, Eric Lindgren, shows sort of global flux spectra, how they vary through the seasons, things like that. But now my postdoc, Brian Green, has spent the last year and a half coming up with a Morley wavelet analysis of these observations. And here is a global plot of what momentum fluxes are transporting in the way of momentum fluxes transported by these gravity waves. This is pretty much global. What I'm showing you here is mean fluxes in boxes of about 5 degrees of latitude by 10 degrees of longitude. This is pretty cool because it's a purely observational estimate. Some of it makes sense. For instance, you can see some very high fluxes over the Andes down over there. Here's the distribution of all fluxes. It's approximately log normal, which matches up with some previous scientific ballooning campaigns. So this is from the French Space Agency, which has had a couple of like a dozen balloons at a time, 2 of them, something like that. And they have one ongoing at the moment. It's called a Stradiol 2. It's mostly over the tropics. So the features of atmospheric gravity waves that we infer from these Loon balloons, we hope are going to be really valuable to provide us input, both for the calibration and uncertainty quantification work, as well as to train something like WaveNet going into the future. We are attempting to do things like decompose these into those set off by orography, so waves because of flow over mountains and everything else. Here showing you just a snapshot of what that looks like. The non-orographic distribution seems to have a bit of a longer tail. Sorry, the orographic distribution has a longer tail, but both of these have a longer tail than previous results, and we think that's because we have geographical coverage that the previous ones did not have. The paper's in preparation. The paper's nearly done. It should be submitted very soon. So that's where we are on that. I also wanted to show you a snapshot of some really high resolution integrations that pretty much resolves the spectrum of these atmospheric gravity waves. This is from the ICON model from the MPI. So ICON stands for icosahedral non-hydrostatic model. And these we have run at 1.5 kilometer resolution. So they're global climate models run at 1.5 kilometer resolution. So it's just an incredible amount of data. We have run it for just a week at a time, but we've run it at every month for a week at a time in 2017. We picked 2017 because there's really good Loon coverage as well in that year. So this is showing you the Drake Passage region along the X direction and the Y direction at the bottom, showing you some really fine scale features associated with the drag. And here I'm showing you ICON in the black. This is the actual drag associated with these breaking gravity waves that force the QBO. This is the QBO region, X and Y in these two. And you can see that the drag in ICON is actually very much larger in some cases than the drag associated with NEMA, which is our climate model. So Laura and I and a couple of others are working on integrating this very high resolution model output with Loon observations to make progress on both the things that I presented earlier on, which is a completely machine learning gravity wave parameterization, and secondly, calibration and uncertainty quantification of existing GWPs based on this data and based on the observational data that I just showed you. So that's kind of where we are on this project at the moment. I thought I would also publicize the project a little bit. So I lead a collaboration of researchers. These are all of my co-PIs who are interested in furthering both our understanding of what atmospheric gravity waves do to climate variability and climate change, as well as coming up with a more physical way of showing what they do in climate models, so improving GWPs themselves. We are funded by Schmidt Futures, who are trying to apparently disrupt the way that climate modeling is done. Here's our webpage. We're about a year into the project at the moment, and I think we've made quite a bit of progress in that 1 year. Between the 8 of us, we typically have openings for PhD students, postdocs, undergraduate researchers, whatever. So if you're interested in high resolution modeling, observations, machine learning, anything to do with these atmospheric gravity waves, and if you'd like to make a real difference to the way that climate modeling is done, we'd love to hear from you. Please send us an email. Okay, do I have time for some weather? No, okay. Fine. I'm just going to skip this part of my talk. I kind of expected that to happen. That's fine. Thanks everyone for your attention. I'm very happy to take questions.